What I usually do, I look at the open loop step response of the system, the open loop process, and try to fit 10 to 20 samples within the rise time. That's a good starting point for choosing the sampling time. And with MPC, you can actually tolerate larger sampling times than you do with other techniques due to the embedded open loop prediction capabilities of the controller. But it pretty much depends on how fast you want to react to set point changes and to disturbances coming in. And of course, and also on the CPU that you have available to solve the optimization problem. Usually, it's enough to have 20, 30 samples because that covers the transient response of the open loop response. But what is very important is the control horizon, which should be limited to small steps. For example, 2 to 4 sampling steps, because that limits the complexity of the QP problem that you are solving. So these are usually dictated by the application. MV constraints are directly dictated by the actuation saturation that you have, so the limits you have on your actuators. And OV constraints are the physical constraints you have on the outputs that you are controlling. And you can also include constraints, it's called MV rate constraints, where you can limit the rate of change of the actuator, of the signals generated for the actuators, which allows you to model slew rate constraints. And you should remember that the more constraints you add in the problem, the more complex it becomes the optimization problem to solve. So you should be parsimonious with the number of constraints you include, and especially if you want to solve the problem explicitly. So what matters is the ratio between the output weights and the weights on inputs and input rates. The larger is this ratio, so the more you weight the outputs compared to the inputs, the more performant will the controller being more aggressive, but most likely the less robust will be the controller. And vice versa, if you want to have a more robust controller, you increase the weights on the inputs compared to the outputs. And what is also important is the length of the prediction horizon. If you want to improve the stability properties of the controller, you should increase the prediction horizon. So the MPC toolbox has a Kalman filter built in that estimates the states based on output measurements. And the filter works for both linear time invariant models and linear time varying models as well.